An object from beyond our solar system, a true interstellar visitor, appears out of the void. In July 2025, it sweeps past Earth in December. We photograph it. We measure its chemistry with the most powerful telescope humanity has ever built. And then, instead of disappearing back into the cosmic dark the way Oumuamua and Borisov did, it DOES and single quotes T. Instead, it turns toward Jupiter. By March 2026. It will pass close enough to the gas giant that some calculations, published calculations, not Reddit fever dreams, suggest gravitational deflection is possible. Maybe even capture. And if the trajectory bends just right, this thing could loop back toward the inner solar system. Toward us. That's the scenario lighting up comment sections, TikTok threads, and even a few peer-reviewed preprints right now. Some call it the return hypothesis. Others are calling it something for stranger. A mothership. An artificial object executing a multi-planet seeding mission. Threading a gravitational needle that no natural comet should be able to hit. Here's what the data actually says. Not what the clickbait says. Not what the doom scroll says. What NASA, ESA, JWST, Hubble, and a handful of very serious astronomers have actually observed and published. Because here's the thing, 3i. Atlas is weird. The chemistry is legitimately unusual. The imaging shows structures that are hard to explain with standard comet physics. The Jupiter flyby is close enough to matter, and the timeline opposition on January 22nd. Jupiter encounter on March 16th gives us to real, testable moments in the next 8 weeks where we'll know a lot more. But between unusual comet and alien mothership, there's a vast canyon of physics, probability, and evidence. And right now, most of the internet is jumping the canyon without a parachute. By the end of this video, you'll know what 3i ATLAS actually is and what we've measured with JWST, Hubble, and ground-based telescopes. Why the CO heavy chemistry is interesting, but not industrial. What the anti-tail and sunward jet images actually show and what they don't. What happens on January 22nd during opposition, and why it matters. What Jupiter's Hill sphere is, why everyone's using it wrong, and what it would actually take to capture or deflect this object. What the March 16th encounter will look like, and what trajectory changes we should expect. Why the return to Earth scenario requires conditions that aren't just unlikely, they're absent from the current data. And yes, we'll talk about the mothership hypothesis, but as a testable claim, not a conclusion. This is not a debunk. This is not a hype piece. This is a walkthrough of what's real, what's speculative, and what we're about to find out. So let's get into it. Welcome to the Cosmic Atlas, the place where we go deeper than the headlines, calmer than the comment sections, and clearer than the clickbait. If you're here, you've probably seen the videos. Maybe you've read the preprints. Maybe someone sent you a breathless text message at 2 a.m. asking if an alien probe is really heading for Jupiter. Or maybe you just saw Interstellar Comet returns to Earth in your feed and thought, wait, what? You're in the right place. We're going to spend the next hour unpacking one of the most fascinating and most misunderstood astronomical events in recent memory. Not because it's definitely alien, not because it's definitely nothing, but because it's actually happening. And the next 2 months are going to give us answers. Here's the deal. If you want the next update after January 22nd, the opposition window, and after March 16th, when 3i ATLAS makes its closest approach to Jupiter, you need to subscribe right now. This story is unfolding in real time. The data is coming in. The observations are scheduled. And we're going to be here, step by step, separating signal from noise. Hit the like button if you want YouTube to know this kind of evidence-based breakdown is worth promoting, because I promise you, the algorithm is flooded right now with 10-minute reaction videos that are 9 minutes of speculation and 1 minute of facts. We're doing the opposite. And please share this with the friend who thinks it's an alien mothership. Not to dunk on them, but to give them the tools to actually evaluate the claim. Because the truth is, some of the anomalies are hard to explain. The question is whether hard to explain means requires new comet, physics, or requires non-natural origins. And we're going to walk that line with precision. All right, let's build the Foundation, July 1st, 2025. Discoverith Atlas Survey Asteroid Terrestrial Impact. Last alert system picks up a new object. Faint. Moving. At first, it's just another dot. Atlas finds a lot of dots, but within days, orbital calculations start coming back strange. The eccentricity is above 1.0. That means hyperbolic. That means it's not bound to the Sun. That means it came from somewhere else. By mid-July. The designation is official. See 2025-01 Atlas. The C means comet. It's showing a coma, a fuzzy envelope of gas and dust. The 2025-01 is just the discovery date code. But soon, a more important label gets attached, 3I ATLAS. The I stands for Interstellar. This is the third object we've ever confirmed to have originated outside our solar system. The first was 1I Oumuamua in 2017, no coma, cigar-shaped or pancake-shaped, depending on who you ask, tumbling fast, gone before we could get a good look. The second was 2I Borisov in 2019, a comet, well-behaved, unremarkable chemistry, exited the solar system on schedule. Now we have 3I, and from the start, it's different. December 19th, 2025, closest approach to Earth. 3I ATLAS reaches its closest point to Earth, approximately 270 million kilometers. For context, that's about 1.8 times the distance from Earth to the Sun, well beyond Mars. It's not a close call. There's no danger, but it's close enough to observe. And observe we do. JWST points its infrared eyes at the coma. Hubble captures visible light images. Ground-based observatories around the world contribute photometry, spectroscopy, astrometry. The data starts piling up. And that's when things get interesting. January 2026. The data drops. Early January. Some of the processed observations start appearing in preprints, press releases, and NASA updates. The chemistry is unusual high CO relative to water. The images show what some are calling an anti-tail or a sunward jet, a structure pointing toward the Sun instead of away from it, which is the opposite of what comet tails normally do. Then, on January 7, 2026, a claim circulates. Hubble imaging processed by citizen scientists appears to show 3 distinct jets emanating from 3I ATLAS, all oriented in directions that don't fit the standard dust pushed by sunlight model. At the same time, orbital projections firm up. 3I ATLAS is heading for Jupiter. Closest approach, March 16, 2026. Distance, approximately 53.56 million kilometers. Give or take 500,000. That's closer than the average distance between Jupiter and its outermost major moon, Callisto. It's well within what's called Jupiter's Hill Sphere, the region where Jupiter's gravity dominates over the Sun's. And that's when the whispers start. What if Jupiter bends its path? What if it doesn't leave? What if it comes back? Why this matters? 3 interstellar objects in a decade sounds like a lot. It's not. It's almost nothing. Before Oumuamua, we had 0. We theorized they existed statistically. They had to. Stellar systems eject comets and asteroids all the time during planetary formation. The galaxy should be full of orphaned debris drifting between stars. But we'd never seen one. Oumuamua changed that, but it also left us with more questions than answers. Was it a comet? An asteroid? Why no coma? Why the weird acceleration? We'll never know. It's gone. Borisov gave us a second data point. Confirmed interstellar comets exist and some of them look like regular comets. Now 3I. If this one is also a normal comet, just with unusual chemistry and structure, that's still huge. It tells us something about the diversity of planetary systems out there. But if it's not normal, if the chemistry, the jets, the trajectory can't be explained with standard models, then we've got a genuine anomaly. And anomalies are where new physics hides. Or, in rare cases where old assumptions break, let's start with what a comet is, because most of the confusion around 3I ATLAS comes from people not realizing how active and dynamic these objects actually are. Comet basics. Dirty snowballs with attitude. A comet is a mix of ice, rock, and organic compounds, frozen volatiles held together in a loose, porous structure. When a comet gets close to the Sun, solar radiation heats the surface. The ices sublimate, they go directly from solid to gas, skipping the liquid phase. This gas expands outward, dragging dust particles with it, forming a cloud around the nucleus called the coma. The coma can be thousands or even millions of kilometers across, even though the nucleus might only be a few kilometers wide. The gas and dust get pushed by solar wind and radiation pressure, forming tails. Usually two, a blue iron tail gas and a white dust tail. These tails always point away from the Sun, not away from the direction of motion. That's why comets can appear to have tails in front of them when they're moving away from the Sun. Comets are also active. They spin. They have jets, localized bursts of gas from specific spots on the nucleus where volatile-rich ice is exposed. They fragment. They change brightness unpredictably. They're messy. Hyperbolic trajectory. What interstellar actually means when we say 3I? Atlas is interstellar. We mean its orbit is hyperbolic eccentricity greater than 1.0. That's a geometry thing, not a speed thing. Elliptical orbits eccentricity less than 1.0 are bound. The object is gravitationally captured by the Sun. It'll loop around forever unless something kicks it out. Parabolic orbits eccentricity exactly 1.0 are the boundary case, just barely unbound. Hyperbolic orbits eccentricity greater than 1.0 are unbound. The object came in with more speed than the Sun's gravity can hold onto. It'll swing around, pick up even more speed from the gravitational assist, and leave for 3I ATLAS. Current calculations put the inbound velocity before the Sun's gravity accelerated it at something on the order of 30 to 35 kilometers per second relative to the solar system. That's fast, but not crazy fast. It's consistent with an object that was drifting through the Milky Way, minding its own business, until it wandered into the Sun's neighborhood. Interstellar does not mean unexplainable. Here's where the first layer of hype comes in. Interstellar sounds exotic. It sounds like it requires a special explanation, but it doesn't. Stellar systems eject objects constantly. During planetary formation, gravitational scattering is the norm. Jupiter-sized planets hurl comets and asteroids outward. Some reach escape velocity. They drift. Eventually, one drifts into another star system. Oumuamua was weird not because it was interstellar, but because it didn't act like a typical comet, no visible coma, but still showed non-gravitational acceleration. Borisov was interstellar and normal, chemically similar to solar system comets. 3.1 ATLAS is interstellar, looks like a comet, but has some features that aren't immediately explained by the standard playbook. That's the key distinction. Unexplained does not equal unexplainable. What we've actually measured so far. Observations of 3I Atlas include astrometry, precise position measurements over time, used to calculate its orbit. Eccentricity is hyperbolic. Perihelion closest to Sun was around late 2025. Trajectory takes it outbound toward Jupiter. Photometry, brightness measurements. 3.1 ATLAS shows typical comet activity brightening as it approached the Sun, now fading as it moves away. No sudden jumps or drops that would suggest fragmentation or explosive outgassing. Spectroscopy, breaking down the light from the coma to see what molecules are present. This is where JWST comes in. Imaging, Hubble and ground-based scopes have captured the coma and tail structure. This is where the anti-tail claims come from. None of this data on its own is extraordinary. Comets are observed like this all the time. The question is whether the specific details, chemistry, structure fit the expected patterns. And that's where we start seeing cracks. What JWST saw in late December 2025. The James Webb Space Telescope turned its infrared instruments toward 3I Atlas. JWST doesn't see visible light, it sees heat, infrared, and in that spectrum, molecules have fingerprints, specific wavelengths where they absorb or emit light. JWST detected 3 primary molecules in the coma. HEO water vapor, expected. Water ice is the dominant volatile in most comets. Carbon monoxide, common in comets, especially those from the outer solar system or interstellar space. CO, carbon dioxide, also common. But here's the thing, the ratio was off. Normal solar system comets tend to have a CO/HEO ratio somewhere in the range of 0.1 to 0.3, meaning for every molecule of CO, you've got 3 to 10 molecules of water. 3.1 ATLAS came in significantly higher. Early reports suggested a ratio closer to 0.6 to 0.8, nearly 1 molecule of CO for every molecule of water. That's not unheard of. Some comets, particularly those from the Oort cloud, show elevated CO, but it's unusual. And when you combine unusual chemistry with interstellar origin, people start asking, why? Why CO? How ratio matters and why it doesn't prove anything. Chemistry tells you about formation conditions. Water ice dominates in the regions where most solar system comets form. Temperatures cold enough to freeze water, but not necessarily cold enough to freeze carbon monoxide, which requires even lower temperatures. CO is in between. It can form in several ways. Direct condensation from the protoplanetary disk in very cold regions. Radiolysis, high-energy radiation, cosmic rays hitting a mixture of water ice and carbon-bearing molecules, creating CO over millions of years. Surface chemistry on ice grains in the interstellar medium before the comet even entered a stellar system. An interstellar comet, by definition, spent time drifting through the galaxy, exposed to cosmic rays. No nearby star, no solar wind protection. That's a perfect environment for radiolysis to enrich CO relative to water. So, a high CO. How ratio in 3i ATLAS? Completely explainable with natural processes. But here's why it's still interesting. If this ratio holds up under further observation, it gives us a chemical signature of interstellar comets, a way to distinguish objects that formed in our solar system from those that formed elsewhere. That's huge for comparative planetology. Why it's not industrial proof now, let's talk about the fringe claim that a high CO ratio suggests artificial production. The idea is that CO is a refined or processed gas, something you'd expect from combustion, respiration, or industrial activity. This claim doesn't hold up for several reasons. CO is everywhere in space. It's on Mars. It's in the atmospheres of Venus and exoplanets. It's in molecular clouds. It's one of the simplest carbon-oxygen molecules. There's nothing inherently artificial about it. No other industrial signatures. If 3i Atlas were an artificial object outgassing propellant or waste heat, we'd expect to see other molecules, methane, nitrogen compounds, NH, complex organics, maybe even metals if we're talking about a physical engine. JWST saw none of that. Just how CO standard comet stuff, just in unusual proportions. Natural mechanisms explain it. You don't need artificial when spent a few million years getting sandblasted by cosmic rays. In interstellar space does the job. The CO anomaly is a real data point. It's scientifically interesting, but it's not evidence of design. What would actually be anomalous if JWST had detected chlorofluorocarbons, CFCs? Industrial refrigerants don't occur naturally. Metallic spectral lines, iron, aluminum, titanium in emission, suggesting hot surfaces or engines. Unusual isotope ratios like enriched deuterium or lithium-6, which could suggest fusion processes, structured radio emissions, not random noise, but pattern signals. Then we'd be having a very different conversation. But JWST saw comet molecules. Unusual proportions, yes, but still comet molecules. What is an anti-tail? Let's define terms, because anti-tail is one of the most misused phrases in this whole discussion. A normal comet tail points away from the sun. Solar radiation and solar wind push gas and dust outward. The tail streams behind the comet relative to the sun, not behind its direction of motion. An anti-tail is an optical illusion. It's a projection effect. Sometimes, when Earth's position relative to the comet's orbit is just right, we see the dust tail edge on. The thick part of the dust sheet, the densest material, lies along the comet's orbital plane. From our angle, that sheet can appear to point toward the Sun, or in a different direction than the main gas tail. Anti-tails are common. They're well documented. Comet Hale-Bopp had one. So, did Comet Androland in 1957 one of the most famous anti-tail photos ever? They look weird, but they're geometry, not physics violations. What is a sunward jet? A jet is different. A jet is a physical stream of gas and dust coming from a localized source on the nucleus. Jets are powered by sublimation. If one side of the comet is getting more sunlight because the nucleus is rotating, or because the surface is uneven, you get jets. Jets usually point outward, following the local terrain and the sun's heating. But in principle, a jet could appear to point sunward if it's being emitted from the night side of the nucleus, and we're seeing it backlit. The nucleus rotation axis is tilted such that a vent facing toward the sun is releasing gas that gets redirected by collisions. In the dense inner coma, there's a secondary process like fragmentation or a subsurface gas pocket releasing that creates a transient emission in an unexpected direction. These are rare, but they happen. They're hard to explain, but not impossible. The January 7th, 2026 Hubble processing claim. Here's where it gets spicy. On January 7th, 2026, processed Hubble images of 3I Atlas started circulating online. Some of these processing efforts came from amateur astronomers and citizen scientists using publicly available Hubble data archives. Yes, you can download raw Hubble data. It's amazing. The claim, 3I Atlas, shows 3 distinct jets, all visible in the processed images, oriented in directions that don't match the expected dust gas tail behavior. One jet appears to point roughly sunward. Another points perpendicular to the orbital plane. The third is more conventional, but broader and more diffuse than you'd expect from a single vent. If confirmed, this is genuinely unusual. Not impossible, just hard to fit into simple models. Plausible comet physics. Explanations. Let's walk through the non-exotic possibilities. 1. Complex nucleus rotation and surface composition. If 3I Atlas has an irregular shape and is tumbling, not just spinning on one axis, different parts of the surface will face the sun at different times. If those parts have different compositions, one patch rich in CO, another in HEO, another in dust, you could get multiple jets with different characteristics. The sunward pointing jet might actually be a dust tail seen edge-on, or a jet from the far side of the nucleus that's getting backlit. Expectation, if true, jets would vary in brightness and structure over hours, days. As the nucleus rotates, we should see periodic changes. 2. Subsurface gas pockets releasing asymmetrically. Comets aren't solid. They're porous. As the surface heats, subsurface ice sublimates, creating pressure. If the overlying crust is weak, it can rupture, releasing a burst of gas. Depending on where and how the rupture happens, the gas could vent in a direction that's not directly away from the sun. This is thought to explain some of the outbursts seen in comets like 17P Holmes, which brightened by a factor of 1,000,000 overnight in 2007, due to a sudden release of subsurface material. Expectation, if true, the jets would be transient. They'd appear, brighten, then fade as the vent depletes. Follow-up images over weeks should show changes. 3. Fragmentation or secondary nucleus. 3I Atlas is actually two objects flying close together. Maybe the nucleus split at some point. You'd see emission from multiple sources. Each fragment would have its own jets, its own coma. From a distance, they'd blur together, but high-resolution imaging like Hubble could resolve them. There's precedent. Comet Schwarzmann-Waldman 3 broke into dozens of pieces. Each piece had its own tail. Expectation, if true, astrometry should show slight positional offsets if the fragments are separating. Photometry might show brightness variations inconsistent with a single rotating body. For magnetic field interaction, exotic but natural. Some comets show evidence of interaction with the interplanetary magnetic field, particularly if the comet is producing a lot of ionized gas. The ions can get caught in magnetic field lines and dragged in unexpected directions. This is rare, and usually only affects the ion tail, not the dust. But if 3I, Atlas has unusually high CO which ionizes easily, and if the interplanetary magnetic field near its orbit had a weird configuration, you might get strange structures. Expectation if true. Iron tail direction would vary with solar wind conditions. We'd need simultaneous solar wind data from spacecraft like DSC-OVR or ACE to check. What would be hard to explain, though, the uncomfortable part? What observations would not fit easily into comet physics? Jets that remain stable over weeks, months without changing brightness or structure. Natural jets should vary as the nucleus rotates and solar heating changes. Jets that point in directions inconsistent with any plausible combination of rotation, venting, and fragmentation. If all three jets point radially outward from a central point in a symmetric pattern, that's weird. Comets are lumpy and chaotic. Perfect symmetry is suspicious, acceleration inconsistent without gassing. If 3I, Atlas changes velocity in a way that can't be accounted for by the measured mass loss rate. From the jets, that's a problem. Oumuamua had this issue. We still don't have a consensus explanation. Jets that correspond to observable surface features that don't show thermal variation. If Hubble or ground-based observations resolve the nucleus, unlikely at this distance, but possible, and we see a jet emanating from a spot that isn't sunlit or recently sunlit. That's hard to explain naturally. We don't have definitive proof of any of these yet. But the January 7th images have people asking the right questions. What is opposition? Opposition is an alignment. It happens when Earth, the Sun, and the target object form a straight line with the Sun on one side and the object on the opposite side. As seen from Earth, the 3I ATLAS opposition occurs on January 22, 2026. Why does this matter? The opposition surge effect when an object is at opposition, the Sun is directly behind us, lighting the object head-on. This geometry does two things: minimizes shadows. Any surface roughness, craters, or texture that normally creates shadows gets fully lit. The object appears brighter than it would at other angles. Backscattering enhancement. For porous, dusty surfaces, light hitting straight on can scatter backward more efficiently than at oblique angles. This is called opposition effect or Seeliger effect in planetary science. Rocky asteroids show this. The moon shows this. It's why a full moon is dramatically brighter than a three-quarter moon. Not just 33% brighter, but comets are surrounded by coma cloud of gas and dust. The coma is diffuse, not solid, so the opposition effect in comets is more subtle. Unless the coma is structured or the nucleus has unusual surface properties. What observers can measure in January 22nd and in the days immediately around it? Professional and amateur astronomers will be watching 3I ATLAS for 1. Brightness spike. 3I ATLAS shows a sharp increase in brightness at opposition, beyond what you'd expect from just the improved viewing geometry it could indicate. A rough, porous surface on the nucleus, more backscatter. Localized dust jets that are aligned toward Earth at this angle, or, in the exotic scenario, a reflective solid surface rather than a diffuse coma. 2. Color changes. Different materials reflect light differently. If the opposition surge is stronger in certain wavelengths, e.g., red versus blue, that tells you about composition. If 3I ATLAS suddenly looks much redder or bluer at opposition, that's data. 3. Polarization. Light reflecting off surfaces gets polarized. Its electromagnetic waves align. Smooth surfaces polarize more than rough surfaces. Icy surfaces polarize differently than rocky surfaces. Polarimetry measurements at opposition can distinguish between a bare nucleus, a dusty coma, and hypothetically a metallic or manufactured surface. Very few amateurs have polarimetry setups, but professional observatories do. For jet behavior. If the jets seen in Hubble images are real and stable, opposition is a chance to see them head-on. If one of those jets is pointing toward Earth, we'd see a brightness spike localized to that jet. If their dust tails seen edge-on, the geometry change might make them disappear or shift. What outcomes would mean? Scenario A. No significant opposition effect. Coma dominates. The nucleus is buried under dust and gas. 3-1. Atlas behaves like a typical comet. The brightness increases slightly due to phase angle, but nothing dramatic. Interpretation: normal comet. The jets might still be real, but they're not evidence of anything exotic. Scenario B: moderate opposition surge. Consistent with porous ice, dust brightness increases by 0.2 to 0.5 magnitudes. Polarimetry shows comet-like behavior. Color doesn't shift much. Interpretation: still consistent with a comet, but suggests the nucleus or inner coma is more structured than average. Interesting, not alarming. Scenario C: strong opposition surge. Unusual polarization or color brightness jumps by a full magnitude or more. Polarimetry shows something inconsistent with dusty coma, maybe low polarization, indicating a smooth surface or high polarization in unexpected wavelengths. The object looks redder or has spectral features that don't fit ice or silica dust. Interpretation: this is where unusual comet starts sliding toward. We need new models. Not proof of artificiality, but enough to warrant serious follow-up and re-evaluation of the nucleus properties. Scenario D: opposition effect plus structural changes in jets. Jets shift, brighten, or disappear at opposition in ways that don't fit rotation or viewing geometry. For example, if one jet vanishes exactly at opposition, that suggests it was an artifact. If a new jet appears, that's harder to explain. Interpretation depends on the specifics, but it would constrain models significantly. Why this is a real test position is predictable. The geometry is fixed. We know exactly where Earth and 3i Atlas will be. If someone claims 3i Atlas is an artificial object with a solid, reflective surface, opposition should produce a telltale signature. If it doesn't, that claim loses weight. If it does, the claim gains a data point, not proof, but something that can't be easily dismissed. This is how science works: predictions, tests, outcomes. January 22nd is one of those moments. The Hill sphere, gravity's zone of influence. Hemogene to massive objects in space, say the Sun and Jupiter, both have gravity, both pull on everything nearby. Now imagine a smaller object, a comet, an asteroid, a spacecraft somewhere between them. That object feels both gravitational fields. But which one dominates? The answer depends on distance. Close to the Sun wins. Close to Jupiter, Jupiter wins. And there's a boundary, a three-dimensional surface where the influence switches. That surface is the Hill sphere. For Jupiter, the Hill sphere extends roughly 50 to 53 million kilometers from the planet, depending on orbital position. It's not a perfect sphere because Jupiter's orbit isn't circular, and the Sun's gravity creates asymmetries. If you're inside Jupiter's Hill sphere, Jupiter's gravity is the primary influence on your orbit. Outside, the Sun dominates. What the Hill radius is about: satellite stability. Hill sphere is fundamentally about stability, specifically the stability of moons. If you want to orbit Jupiter like Callisto, Ganymede, or any of the dozens of irregular moons, you need to be well inside the Hill sphere. Otherwise, the Sun's gravity will perturb your orbit over time, eventually pulling you away. Jupiter's outermost moons are about 20 to 30 million kilometers out, well inside the Hill radius. They're stable for now. Objects near the edge of the Hill sphere, but not fully inside, can have complicated trajectories. They might orbit Jupiter for a while, then get perturbed out. Or they might get temporarily captured, orbit a few times, then escape. This is called temporary capture, and it happens. In 2006, an asteroid named 2006H was temporarily captured by Earth for about a year before escaping. Saturn's moon Phoebe might be a captured Kuiper Belt object. But here's the key: the Hill radius does not mean automatic capture. Why Hill radius is not auto-capture? Capture requires energy loss. When an object approaches a planet, it speeds up gravitational acceleration. If nothing slows it down, it swings around the planet and leaves with the same speed it arrived. To stay captured, the object needs to lose energy. In the Jupiter system, there are a few ways this can happen. Atmospheric drag. If the object passes through Jupiter's upper atmosphere, friction slows it down. But 3I ATLAS is passing 53 million kilometers out nowhere near Jupiter's atmosphere-moon interactions. If the object passes close to a moon, the moon's gravity can steal energy. This is how some of Jupiter's irregular moons probably got captured. But you need to pass very close to a moon within a few 100,000 km. 3.1 ATLAS isn't predicted to do the tidal effects. If the object is close enough, Jupiter's gravity can stretch it, generating heat through internal friction. That heat is energy lost from the orbit. But again, 53 million km is way too far for this to matter. Without energy loss, you don't get capture, you get a gravitational deflection. The path bends, the velocity changes direction, but the object leaves. And yet, the numbers line up. Here's where it gets interesting. The fact that 3I Atlas is passing right at the edge of Jupiter's Hill sphere isn't suspicious on its own. Lots of objects pass through that region. The asteroid belt, the Trojans, occasional comets. What's interesting is that 3I ATLAS's Interstellar already unusual, passing close to Jupiter at a specific distance and speed, doing so during a transfer window that, if deflection occurs in a specific way, could result in a trajectory that returns it to the inner solar system. And some researchers, most notably Avi Loeb at Harvard, have pointed out that the probability of this alignment is low, not impossible, not requires intelligent design, but low enough that it's worth calculating carefully. Because here's the thing, if you wanted to enter the solar system, study multiple planets, and use Jupiter as a gravitational brake, this is almost exactly the trajectory you'd choose. That doesn't mean that's what's happening. Natural coincidences occur, but it means the question is legitimate. So let's look at what the Jupiter encounter actually involves. The set upon March 16, 2026. 3.1 ATLAS will reach its closest approach to Jupiter. Distance 53.56 million kilometers plus or minus 0.45 million kilometers, depending on refinement of the orbit as new observations come in. For context, Jupiter's radius 71,492 km. Jupiter to Callisto outermost Galilean moon approximately 1.88 million km. Jupiter to its farthest known irregular moon approximately 28 million kilometers. Jupiter's Hill radius 5053 million km. So 3I Atlas is passing just inside or right at the boundary of Jupiter's gravitational dominance zone. Relative speed. Context is the critical part. 3I Atlas is moving fast relative to Jupiter. Estimates put the encounter velocity at roughly 12 to 15 kilometers per second relative to Jupiter. For comparison, Jupiter's escape velocity from its surface 60 kilometers per second. Jupiter's orbital speed around the Sun 13 kilometers per s. So 3.1 Atlas is approaching at a speed comparable to Jupiter's own orbital motion, but not dramatically faster. That's actually somewhat slow for a hyperbolic interstellar object. What happens during the flyby? Jupiter's gravity will bend 3I ATLAS's path. This is a gravitational slingshot or gravity assist, the same technique spacecraft use to gain speed. But the effect depends on the geometry. Leading side encounter object passes in front of Jupiter's motion. The object gains speed. It gets a boost forward. Trailing side encounter object passes behind Jupiter's motion. The object loses speed. Jupiter steals some of its momentum. The 3I ATLAS. The trajectory suggests a trailing side encounter. It's coming from behind Jupiter relative to the planet's motion around the Sun. That means Jupiter will slow it down in the Sun's reference frame. How much deflection? The deflection angle depends on closest approach. Distance 53.56 million kilometers. Relative speed 12 to 15 kilometers per second. Jupiter's mass 898 times 10 kilograms. Using the standard gravity assist formula, the deflection is probably in the range of 5 to 15 degrees. That sounds small, but over interstellar distances, a few degrees is enormous. It's the difference between escaping the solar system and looping back toward the inner planets. Energy change more important than deflection is energy. Will 3i ATLAS lose enough speed to become gravitationally bound to the Sun? Right now, it's on a hyperbolic trajectory. Its total energy kinetic plus potential is positive. That means it will escape. If the Jupiter encounter reduces its speed enough, the total energy could become negative. That would make the orbit elliptical. Bound, it would no longer leave the solar system. Preliminary calculations suggest this is possible but unlikely. The encounter is far enough out, and the speed high enough, that most models predict 3i Atlas will remain hyperbolic just with a different exit trajectory. But the error bars are real. Small uncertainties in the current orbit, small variations in how much outgassing thrust 3i ATLAS produces, or unexpected perturbations from other bodies, could shift the outcome. Post-encounter observations after March 16th. Observers will measure new trajectory. Within days to weeks, astrometry will pin down the new orbital elements. We'll know the eccentricity still hyperbolic or now elliptical. Velocity change. Doppler spectroscopy and astrometry will measure the speed change. Did it lose 1 kilometer per second? 3 kilometers per second? More? Activity change. Did the gravitational stress from the flyby trigger new outgassing? Fragment the nucleus? Change the coma structure? Jupiter's gravity is strong enough to create tidal stress even at 53 million kilometers, especially if the nucleus is fragile. The possible outcome is outcome 1. Hyperbolic exit. Slightly deflected 3i ATLAS leaves the solar system, but on a different path than it came in. Eccentricity remains above 1.0. Speed is reduced, but not enough to bind it. Interpretation, normal gravity assist. Interesting for dynamics, but doesn't change the interstellar visitor status. Outcome 2, barely bound eccentricity just below 1.0. The encounter reduces speed just enough that 3i ATLAS becomes bound to the Sun, but on an extremely eccentric, long-period orbit. Perihelion might still be near Jupiter or beyond. Aphelion could be hundreds of out. The object would technically return, but on a time scale of centuries or millennia. Interpretation, this will be unusual. Not impossible. Capture happens but rare for an object this size with this velocity. Outcome 3, tighter elliptical orbit. Perihelion in inner solar system thing counterchanges the trajectory, such that 3i Atlas becomes bound and its new perihelion is in the inner solar system Mars, Earth, Venus region. This is the return hypothesis scenario. Interpretation, this is where the math gets really tight. For this to happen, you need precise encounter distance to close or too far, and the deflection angle is wrong. Precise velocity to fast, no capture. Too slow. Capture into outer system. Precise timing encounter has to happen at the right point in Jupiter's orbit. Closing parenthesis. The probability of all 3 aligning naturally is debated. We'll get to that in the next section. 3 distinct claims. Stop conflating them. The internet has mashed 3 different scenarios into one panic smoothie. Let's separate them. Claim 1. Gravitational deflection. Jupiter's gravity will alter 3i ATLAS's trajectory. This is guaranteed. This is physics. The question is only how much and in what direction. Status confirmed. It will happen. The only question is magnitude. Claim 2. Gravitational capture. Jupiter's gravity will bind 3i Atlas to the solar system, changing its orbit from hyperbolic to elliptical. Status possible, but requires specific conditions. Most models say no, but the uncertainties are real. Claim 3. Return to Earth. Soon 3i Atlas will become bound and its new orbit will bring it close to Earth within months or years. Status requires deflection and capture and a specific orbital geometry. This is the compound probability claim. This is where most models say extremely unlikely. Most headlines and videos skip straight to Claim 3, treating it as if Claim 1 implies Claim 3. It doesn't. Why capture is hard. The energy problem. Let's do the energy accounting. When 3i Atlas entered the solar system, it had kinetic energy from its speed, gravitational potential energy negative, Because it's in the Sun's gravity well, the total was positive, meaning more kinetic than the gravity well could hold. As it fell toward the Sun, it sped up. Kinetic energy increased, potential energy became more negative. Total stayed positive. Now it's leaving. It's climbing back out of the well. Kinetic energy is dropping, potential energy is increasing, becoming less negative. At infinity, it would still have some speed left over. That's what hyperbolic means. To capture it, you need to remove that excess kinetic energy. Jupiter can't create or destroy energy, it can only redirect it. It can change velocity, direction, and magnitude in the Jupiter-Sun system's reference frame. But the total energy in that frame is conserved during the flyby. The only way capture works is if the flyby geometry is such that the velocity vector after the encounter points in a direction where the Sun's gravity can hold it, or some additional force outgassing, fragmentation. Collision removes energy during or after the flyby. What would be required for a return to Earth scenario for 3I Atlas to end up on an orbit? That brings it back to Earth's neighborhood, say, within 1 astronomical unit of the Sun within a few years. You'd need, requirement 1, capture into an elliptical orbit. This requires the post-Jupiter velocity to be below solar system escape velocity at that distance. Requirement 2, perihelion closest point to Sun near Earth's orbit. The deflection angle has to be such that the new orbit's perihelion is around 1 astronomical unit. Too little deflection, and perihelion stays out near Jupiter or beyond. Too much, and it crashes into the Sun or swings wildly eccentric. Requirement 3, inclination change. 3.1 ATLAS is coming in at a relatively high inclination to the solar system. Plane may be 30 to 40 degrees, depending on final orbital refinement. To hit Earth's neighborhood, the inclination needs to drop, or the timing of perihelion passage needs to align with. When Earth crosses the comet's orbital plane, inclination changes are hard. They require out-of-plane forces. Jupiter can do this, but again, the geometry has to be very specific. Requirement 4, orbital period short enough to matter. If 3I ATLAS ends up on a 500-year orbit, sure, it'll return, but not in any meaningful human time scale. For the return scenario to be alarming, the period needs to be short, say, 5 to 20 years. That means a semi-major axis in the range of Jupiter's orbit or closer. Putting numbers to it and back of the envelope orbital mechanics to capture into a 10-year orbit. 3I Atlas needs to lose roughly 30 to 40% of its kinetic energy relative to the Sun during the Jupiter encounter. The expected energy change from a 53 million kilometers flyby at 12 to 15 kilometers per second is maybe 10 to 20%. That's not enough to make up the difference you'd need. The current velocity estimate to be wrong, possible error bars exist. The encounter distance to be closer than predicted. Also possible orbit refinement continues. Additional forces outgassing thrust. Fragmentation to assist. Or you'd need the encounter to happen in a very specific geometry where the velocity change isn't just a magnitude shift, but a precise redirection that puts 3I Atlas onto a resonant orbit. NASA is not hiding anything. NASA's FAQ on 3I Atlas, published in December 2025 and updated in January 2026, explicitly addresses the return question. Their position, the Jupiter encounter will deflect the trajectory. Current models do not predict capture. If capture occurs, the most likely result is a long-period orbit, not an immediate return. Continued observation is ongoing. This is not a cover-up. This is uncertainty. Orbital mechanics has error bars. Observations have noise. The comet is actively outgassing, which creates non-gravitational forces that are hard to model precisely. NASA is being appropriately cautious. Saying probably won't return is not the same as definitely won't return. But saying might return is not the same as will return. The difference matters. The coincidence question here's where Avi Loeb's argument comes in. If you assume 3I ATLAS is a natural comet, the probability of it entering the solar system on an interstellar trajectory, passing close to Earth not impacting, but close enough to observe. Then passing Jupiter at a distance and speed that could result in capture or significant deflection, and doing so at an angle that could return it to the inner system. That compound probability is very low. Estimates vary, but ballpark 1 in a million, maybe 1 in 10 million, depending on assumptions. Does that mean it's artificial? No. Low probability events happen. The lottery has million-to-1 odds and people win. But it does mean we should check carefully. If the trajectory changes after Jupiter are consistent with natural deflection, fine. Coincidence confirmed, move on. If the changes are not consistent, if the deflection is larger than predicted, or in a direction that doesn't fit, then we have a genuine anomaly. March 16th will tell us. The hypothesis as stated by proponents, some researchers, including Avi Loeb, have floated the possibility not as a conclusion, but as a testable hypothesis that 3I, Atlas could be an artificial object. Executing a multi-planet observation or seeding mission. The logic goes. An interstellar probe entering the solar system would want to study multiple planets. The most efficient way to do that is a gravity assist. Trajectory use one planet's gravity to swing toward another. Jupiter is the obvious choice for such a maneuver. It's the most massive planet, provides the biggest gravity assists, and is near the entrance to the inner solar system. If you wanted to study Jupiter and then return to the inner system Earth, Mars, Venus, you'd design a trajectory almost exactly like 3I. Atlas !says. Add to that the unusual chemistry CO heavy coma, the possible sunward jet or anti-tail structures, the fact that we've only seen 3 interstellar objects ever, and Oumuamua was also weird, and you get, what if this isn't coincidence? What if this is intent? Why seeding Jupiter specifically? Jupiter has 95 known moons. Most of the outer ones, the irregular moons, are captured objects. They're not spherical. They're chunks of rock and ice 1 to 10 kilometers across. Probably asteroids or comets that got caught by Jupiter's gravity millions of years ago. If you were an advanced civilization wanting to place monitoring stations or probes in the solar system, Jupiter's irregular moons are perfect. They're stable. They're numerous. They're hard to detect unless you're specifically looking. And Jupiter's environment, radiation, magnetic field, ring system is scientifically rich. The seeding scenario suggests, what if 3I? Atlas releases small payloads during the Jupiter flyby, objects small enough that we can't resolve them from Earth, but large enough to be functional probes. Those objects could use small thrusters or even just outgassing to adjust their trajectories and insert themselves into orbit around Jupiter. Or they could already be in orbit, placed by a previous mission. And 3I, Atlas is a resupply or communication relay. Sound crazy? Sure, but let's treat it seriously. What would we expect to observe if this were true? 1. Velocity changing consistent with outgassing of 3I. Atlas is shedding mass to slow itself down, releasing probes. Ejecting material, there would be a measurable thrust. Natural outgassing creates thrust to Oumuamua's acceleration was probably this. But natural outgassing should correlate with solar distance and coma brightness. If 3I, Atlas shows thrust that doesn't correlate, like it slows down more than the observed coma mass loss predicts. That's anomalous. This is measurable. We just need precise astrometry before and after the Jupiter encounter. 2. Discrete events during flyby. If payloads are released, we might see brightness flashes, small explosions or propulsion burns, fragments separating from the main coma, sudden changes in coma structure or outgassing rate. These would need to be observed during the flyby, which is hard. Jupiter is far, and 3I, Atlas will be moving fast. But it's not impossible. Large ground-based scopes and Hubble could do it. 3. New objects appearing in Jupiter's irregular moon population months or years after the encounter. Surveys of Jupiter's outer moons might detect new objects. This happens naturally. Astronomers discover new irregular moons periodically as surveys improve. But if we find several new small moons with orbits that trace back to close encounters, with 3I ATLAS's trajectory around March 16, 2026, that's suspicious. 4. Non-gravitational trajectory changes that require directed thrust of 3I ATLAS's post-Jupiter orbit. Changes in ways that can't be explained by gravity alone, like if it makes a course correction weeks after the flyby, that would be strong evidence of propulsion. Natural comets can't do that. They can outgas, which creates thrust, but that thrust is radial outward from the nucleus and depends on solar heating. It doesn't do precise course corrections. Why natural fragments can't do the seeding job is the key physics problem. If 3I ATLAS naturally fragmented, the nucleus split, the pieces would have nearly the same velocity. They'd drift apart slowly, but they'd all still be on hyperbolic trajectories. To go from hyperbolic flyby to captured moon, each fragment would need to lose velocity independently. A lot of velocity. That requires thrust. Natural outgassing could provide some thrust, but it's not steerable. You can't aim it. You can't control when it fires. To insert multiple fragments into stable orbits around Jupiter, each targeting a different orbital resonance or inclination, you'd need precise delta-v burns. That's propulsion. That's not natural. So if we detect new moons around Jupiter after March 16th, and if their orbits are tightly clustered or show signs of deliberate targeting, that's very hard to explain naturally. The counterarguments why this is still extremely unlikely: 1. No other artificial signatures. If 3I Atlas is a probe, we'd expect radio transmissions. We've looked, nothing. Unusual thermal signatures. JWST would have seen waste heat. From power systems, it didn't. Non-random surface features. We haven't resolved the nucleus, so can't check yet. The absence of these isn't proof of absence, but it's a point against. 2. A Cam's Razor unusual comet requires bending 1 or to natural explanations. Alien Mothership requires inventing an entire civilization, interstellar travel technology, and a motivation to seed solar systems. 1 is vastly simpler. 3 sample size. We've seen 3 interstellar objects. 2 were weird. That's a 66% weird rate. But 3 is a tiny sample. We can't conclude interstellar objects are usually artificial from 3 data points. With better surveys like LSST, which comes online soon, we'll probably detect dozens of interstellar objects per year. Most will likely be normal. The weird ones will stand out more clearly. 4. The Fermi paradox of spacefaring civilizations are common, and they're sending probes to every star system. We should have detected them by now. The fact that we haven't or haven't definitively suggests either they're not common, they're not sending probes, or the probes are extremely stealthy. Asterisk 3I ATLAS is not stealthy. We can see it. So, if it is artificial, it's either old and broken, or it's meant to be seen. How to think about this mothership scenario is not a conclusion. It's a hypothesis. And the thing about hypotheses is, you test them if post-Jupiter observations show trajectory consistent with natural deflection, activity consistent with comet outgassing, no discrete objects separating, no new Jupiter moons with suspicious orbits, then the hypothesis is falsified. Move on. But if we see anomalies, thrust that doesn't fit, fragments that capture themselves, anything that violates conservation of energy or momentum without a natural mechanism, then the hypothesis gains weight. That's not proof, but it's enough to warrant deeper investigation. And honestly, that's exciting either way. Either we learn something new about comet physics, or we learn we're not alone. Both are wins for science. What Juno is? Juno is a NASA spacecraft that's been orbiting Jupiter since July 2016. Its mission: study Jupiter's atmosphere, magnetic field, interior structure, and polar regions. Juno's orbit is highly elliptical. It swings close to Jupiter within 5,000 kilometers of the cloud tops, then loops back out to about 8 million km, completing one orbit every 53 days. It's not designed to observe distant objects. It's designed to study Jupiter. But 3I ATLAS will pass within 53 million kilometers of Jupiter on March 16th. That's 6 to 7 times farther than Juno's maximum orbital distance. So from Juno's perspective, 3I ATLAS is far. Like binoculars from Earth far. What instruments Juno has? Juno carries JunoCam visible light camera. Public outreach instrument. Takes color images of Jupiter's clouds. Resolution is great for Jupiter close-ups, but it's not a deep space telescope. Geron Jovian infrared auroral mapper. Infrared imager and spectrometer. Designed to study Jupiter's auroras and heat emissions. Could, in theory, detect a warm object at a distance if it's bright enough in IR. Microwave radiometer MWR measures microwave emissions from Jupiter's deep atmosphere. Not relevant for 3I. Atlas magnetometers MAG measures magnetic fields. Could detect disturbances if 3I. Atlas has an ion tail that interacts with Jupiter's magnetosphere, but at 53 million kilometers unlikely. Waves, JEDI particle and plasma instruments again. Designed for Jupiter's magnetosphere, not useful for a distant comet. Gravity science uses Juno's radio link to measure Jupiter's gravitational field. Can't detect 3I. Atlas. Could JunoCam image 3I? Atlas? Maybe. If Juno's orbit puts it in a position where 3I. Atlas is in the camera's field of view, the camera is pointed in that direction. It's manually commanded, not automatic. And 3I. Atlas is bright enough to stand out against the star field. But JunoCam has a limited field of view and is optimized for close-up imaging of Jupiter's clouds, not distant point sources. Even if it captured 3I ATLAS, it would be a faint dot. You wouldn't see structure. You wouldn't see the coma. Just a point. Ground-based telescopes on Earth would get better images. Could Geron detect 3I? Atlas? More likely. Geron operates in infrared, which is where comets glow due to heat from the sun and from sublimating. If Geron were pointed at 3I ATLAS during the flyby, it might detect the comet's thermal signature. It could measure brightness and get a rough temperature. But again, JIRAM's field of view is narrow. It's designed to scan Jupiter's poles, not track distant objects. Pointing it at 3I, Atlas would require mission planners to deliberately schedule it. But also, mission schedule really shares the catch. Juno's extended mission runs through September 2025. According to NASA's publicly available mission timeline as of early 2024. Closing parenthesis. The Jupiter flyby of 3I ATLAS is March 2026. NASA has proposed further extensions and Juno is still healthy, so it's likely to still be operational. But there's no guarantee, and even if it is, the observation schedule is packed with Jupiter science. Adding a turn and look at the Comet maneuver would compete with primary mission objectives. It's possible NASA will do it. It would be scientifically valuable. But it's not automatic. What Juno could contribute if tasked if NASA decides to point Juno's instruments at 3I. Atlas during the encounter, the best contributions would be unique viewing angle. Juno sees 3I. Atlas from Jupiter's perspective, not Earth's. That gives stereoscopic data combine Juno's observations with Earth-based observations, and you can triangulate 3D structure in the coma. In situ magnetosphere measurements. If 3I ATLAS's coma or ion tail interacts with Jupiter's magnetosphere, unlikely at that distance, but possible, Juno's particle instruments would detect it. That would tell us about the ionization state of the coma. Infrared thermal data. Geron could measure the thermal emission from the nucleus if it resolves it or from the coma, combined with JWST's data that refines models of composition and activity. But realistically, Juno's contribution would be supplementary. The heavy lifting will be done by Earth-based observatories, Hubble and JWST. The bottom linear might observe 3I ATLAS. It's technically possible, but it's not a guarantee, and it wouldn't revolutionize our understanding compared to what we're already getting from Earth. And space-based telescopes don't count on Juno to prove or disprove the Mothership hypothesis. That's not what it's designed for. What is UFM? In 2003, a team of astronomers led by Scott Shepard discovered a small, faint moon orbiting Jupiter. They named it UFM, pronounced Eupheme after a minor Greek goddess associated with good omens and praise. UFM is about 2 kilometers in diameter. That's tiny, smaller than most city neighborhoods. It orbits Jupiter at an average distance of roughly 19.4 million kilometers, taking about 583 days to complete one orbit. That orbit is retrograde. It goes the wrong way around Jupiter compared to the Galilean moons, highly eccentric, not circular. It swings closer and farther, highly inclined, tilted relative to Jupiter's equator. These characteristics are the signature of a captured object. UFM didn't form with Jupiter. It was born somewhere else, probably in the asteroid belt or Kuiper belt, and got snagged by Jupiter's gravity millions of years ago. The Anunk group UFM is part of a family called the Anunk group, a cluster of about 20 small moons, with similar orbits. They're all retrograde, all irregular, all tilted. The leading theory: these moons are fragments of a single parent body that got captured, then shattered either by a collision or by tidal stress. From Jupiter, the pieces stayed in similar orbits, forming a group. Think of it like a cosmic car crash in slow motion, frozen in orbit. Why this matters for 3I, at last the existence of UFM and the Anunk group proves that capture happens. Jupiter has captured objects before, many times. Dozens of irregular moons testify to that. So, the question isn't whether Jupiter can capture things, it's how often and under what conditions. The irregular moons we see now were probably captured billions of years ago, when the solar system was younger and more chaotic. The asteroid belt was denser. More objects were flying around. Jupiter swept through the debris field and caught what it could. Today, the solar system is calmer. Fewer objects, fewer opportunities. But it's not zero. If 3I, Atlas, were captured and became a new irregular moon, it wouldn't be unprecedented. It would be rare, but not impossible. Don't oversell the threading a needle metaphor. Here's where some of the online discourse goes off the rails. People say, what are the odds that 3I ATLAS passes exactly at the right distance and speed to be captured? That's like threading a needle from across the galaxy. Sounds dramatic, but it's misleading. First, the capture zone isn't a pinpoint, it's a range. Jupiter's Hill sphere is 50 million kilometers wide. That's a huge target. Sure, only a fraction of that zone results in stable capture, but it's not a single trajectory. Second, we don't know how many interstellar objects pass through the solar system and don't get captured. Maybe 3I ATLAS is one of thousands. We're only seeing it because it did happen to come close. This is survivor bias. We notice the ones that hit the target. We don't notice the misses. Third, UFM and the other Anunk moons weren't threaded either. They were captured during a chaotic era when Jupiter was still clearing its orbital zone. The process was messy, not precise. So yes, 3-1. Atlas passing Jupiter at capture range distance is low probability. But it's not astronomically low. It's within the realm of natural occurrence. What would be weird, what would be genuinely strange is if 3I, Atlas, gets captured into a stable, low eccentricity orbit on the first pass. Natural captures are usually highly eccentric. Circularizing takes time and repeated perturbations. Gets captured into an orbit that's prograde same direction as Jupiter's major moons. Natural captures tend to be retrograde. Gets captured and then changes its orbit after capture in ways that can't be explained by gravitational interactions with Jupiter's existing moons. Those would suggest something beyond natural capture. But if 3I ATLAS just gets deflected, or gets captured into a wild, eccentric, retrograde orbit, that's normal. All right, let's talk about the elephant in the comment section. If you've spent any time reading about 3I ATLAS online, you've probably seen the name Bob Vanga. Bob Vanga was a Bulgarian mystic who died in 1996. She was blind and claimed to have psychic visions over her lifetime. She made thousands of predictions, some vague, some specific, many wrong. A few coincidentally right. The internet loves Bob Vanga. Every year, lists of her predictions circulate, and every year, people retrofit current events to match them. For 2026, one of the widely cited predictions is something like, a visitor from the stars will arrive, and humanity will face a test. Guess what shows up in early 2026? 3-1. Atlas.q to conspiracy theories. Why people latch onto prophecy narratives. This is sociology, not astronomy, but it's worth understanding. Humans are pattern-seeking machines. We're wired to find meaning in chaos. When something unusual happens, a comet, a pandemic, an eclipse, we look for explanations. If we don't have a scientific one, we reach for narrative ones: prophecy, fate, omens. Prophecies are especially seductive because they're vague enough to fit anything. A visitor from the stars could mean a comet, an asteroid, a spacecraft, aliens, or even a metaphor for a new idea or technology. When you have thousands of predictions, some will line up with events by pure chance. That's not magic. That's statistics. The retcon problem here is the thing about Vanga's predictions. Most of them were never written down during her lifetime. They were passed along orally, translated multiple times, embellished, and eventually posted online decades after her death. There's no original source, no authenticated list. What you see on TikTok or in tabloid articles is a game of telephone. Someone heard someone say Vanga said something about stars. And now, retroactively, that gets applied to 3i Atlas. This is called retrofitting. You take a vague statement, wait for something to happen, then claim the statement predicted it. It's not predictive power. It's hindsight bias. Does this mean 3i Atlas isn't worth paying attention to? No, absolutely not. 3i Atlas is worth paying attention to because of the data, not because of prophecies. The chemistry is unusual. The trajectory is interesting. The Jupiter flyby is a real test. These are observable, measurable, falsifiable claims. Prophecy is none of those things. But here's why I'm even mentioning this. Because for a lot of people, the prophecy is the hook. It's what brought them to the story. And that's fine. If Vanga gets someone interested in orbital mechanics, JWST spectroscopy, and gravitational physics, that's a net win for science literacy. Just don't let the prophecy replace the data. The psychology of apocalypticism is another layer here. Notice how the prophecy is framed. Humanity will face a test. Apocalyptic language. Existential stakes. Why do these narratives persist? Because they make us feel like we're living in important times. Like history is happening now and we're part of it. And you know what? Maybe we are. Climate change, AI, nuclear proliferation, there are real, non-mystical challenges. But projecting that onto a comet is displacement. It's easier to worry about a cosmic visitor than about systemic, slow-moving, human-caused problems. Keep it in perspective. 3i Atlas is not an omen. It's not a test. It's a comet. It might be an unusual comet. It might even be an artificial object, low probability. But we'll check. But it's not fate. It's physics. And physics, unlike prophecy, gives us answers. You've made it this far. You understand the data. Now here's what to actually pay attention to. The next 2 months are going to be noisy. Every new image, every preprint, every Twitter thread is going to get amplified. Most of it will be speculation layered on speculation. Here's your filter. These are the observations and outcomes that actually matter. Checkpoint 1. January 22nd, 2026. Opposition. What to watch for? Brightness measurements. Did 3i Atlas show a significant opposition surge? If yes, how much? Compare to predictions. Polarimetry results. Did any observatories publish polarization data? What does it say about surface versus coma? Jet structure changes. Did the sunward jet or triple jet features change, disappear, or intensify at opposition? What outcomes mean? No major surge, stable jets gives consistent with a comet. Interesting, not anomalous, moderate surge. Comet-like polarization gives still consistent with unusual comet. Strong surge, unusual polarization. Jet changes gives anomalous. Warrants re-evaluation of nucleus properties. Where to find data? NASA updates. NASA GOV, feature or GSFC pages, ESA press releases, preprint servers arxiv.org. Search 3i Atlas, Astronomer Twitter, X accounts Avi Loeb, Scott Shepard. Others in the field. Checkpoint 2, March 16th, 2026, Jupiter encounter. What to watch for? post-encounter orbit. What's the new eccentricity? Still hyperbolic E greater than 1 or elliptical E less than 1? Velocity change. How much speed did 3i, Atlas lose or gain? Does it match models? Activity changes. Did the flyby trigger outbursts, fragmentation, or new jets? Discrete objects. Did anything separate from the main nucleus? What outcomes mean? Hyperbolic exit. Velocity change matches predictions, gives natural deflection. Story over scientifically interesting, but no return. Captured into long period orbit E less than 1. But perihelion beyond Jupiter gives unusual but explainable. Captured objects happen. Captured into short period orbit perihelion in inner solar system gives very unusual. Requires detailed trajectory analysis to see if natural mechanisms suffice. Velocity change exceeds predictions or trajectory changes inconsistent with gravity gives anomalous. Suggests non-gravitational forces outgassing or something else. Discrete objects detected, especially if they insert into Jupiter orbits, gives red flag. Investigate immediately. Where to find data? NASA, JPL. Horizon's system orbital elements updated as new observations come in. Minor Planet Center. IAU's clearinghouse for small body observations. Preprint servers. Major observatory press releases. ESO. Keck, Hubble, JWST. Checkpoint 3, April-May 2026. Post-Jupiter observation campaign. After the encounter, there will be a flurry of follow-up observations. This is when we'll get the clearest picture. What to watch for? Refined orbit. Error bars shrink. We'll know for sure whether it's bound or unbound. Long-term activity. Is 3i, Atlas still outgassing? Fading? Brightening unexpectedly? Spectroscopy follow-up. New JWST or ground-based spectra. Does the chemistry change post-Jupiter? Moon surveys. Are astronomers checking Jupiter's irregular moons for new additions? What would falsify the return hypothesis these observations would definitively rule out? A return to Earth. Eccentricity remains greater than 1.0 with small error bars. Not bound. It's leaving. Velocity change matches natural gravitational deflection models. No unexplained thrust. PERIHELION if captured is beyond 3 astronomical units, even if bound. It won't come near Earth. Activity fades predictably with solar distance. No anomalous outbursts or thrust. If all four are true, the return hypothesis is dead. What would escalate? Not normal comet. These would suggest something beyond standard comet models. Velocity change significantly exceeds gravitational models, with no corresponding increase in coma mass loss. Thrust without visible propellant. Trajectory changes after the Jupiter encounter that require directed acceleration. Course corrections. Discrete objects confirmed separating and inserting into Jupiter orbits. Deployment event. Chemical signatures that don't fit natural comet composition. We'd need new JWST spectra showing something truly weird like industrial byproducts. Radio emissions, heat signatures, or surface features inconsistent with natural bodies. Direct evidence of artificiality. If any one of these happens, we're in call an urgent meeting territory. If multiple happen, we're in rewrite the textbooks territory. Engagement prompt. What's your prediction? All right, let's make this interactive. Drop a comment below with your prediction for the March 16th encounter. Choose one. A hyperbolic exit, slight deflection, normal comet. Boring but most likely. B barely captured, long period orbit, returns in 500 years. Unusual, still natural. C captured into short period orbit, returns to inner system within 10 to 20 years. Very unusual, needs explanation. D trajectory change suggests non-gravitational forces. Anomaly confirmed. Exciting and alarming. E discrete objects detected. Mothership hypothesis gains weight. Rewrites everything. Tell me which one you think will happen and why. Let's see who gets it right. And hey, if you predicted E and you're wrong, you owe the comment section a pizza. Deal. We've covered a lot. If you're still here, you now understand 3i. Atlas better than most of the internet. Here's what we know. 3I ATLAS is an interstellar comet discovered in July 2025. It passed Earth safely in December. JWST detected unusual CO2-water chemistry strange, but still explainable by natural processes. Hubble images suggest possible jets or an anti-tail, though it's not yet clear if these are real structures or imaging artifacts. On March 16, 2026, the object will pass Jupiter at about 53.56 million kilometers inside Jupiter's Hill sphere, meaning gravitational deflection is guaranteed. What we don't know is what makes this interesting. Will that deflection be enough to capture it into a bound orbit? If so, what will that orbit look like? Will it return to the inner solar system? Are the jets real, and could anything separate from the nucleus? What's next is critical. January 22nd brings opposition when brightness, jet behavior, and polarization can be tested. March 16th is the Jupiter encounter. After that, refined orbits and follow-up observations. Ignore the hype prophecies, cover-ups, panic. Focus on what's worth studying, the chemistry, the jets, and the post-Jupiter trajectory. This isn't a closed case. It's science unfolding in real time. See you on January 22nd.